This information is for technicians who service the automotive products of the Ford Motor Company.
This videotape has been prepared to help you diagnose and correct problems with the electrical power supply system. The system that we will be working with consists of the battery, the alternator, the regulator, and the connecting wires and switchers. During this program, we'll look at each part of the system on cars that represent the kinds of problems that you are most likely to see. There are really only a few problems that indicate trouble with the charging system.
First, of course, the battery is dead, flat dead, so that it will not operate the starting motor, the horn, lights, or any other electrically powered accessory. It won't even click the starting motor relay. Then there is the slow cranking battery. It cranks the engine all right, but it often runs down before the engine starts. Then there is the charging system that behaves great all day, but the battery runs down overnight. If the engine doesn't start next morning with the first few turns of the starting motor, the battery quickly fades to where a service call is in order. When you are faced with a problem of a dead or weak battery, and you want to quickly find which part or assembly of the system is causing the trouble, first, verify the complaint. Once you have convinced yourself that problems do exist, give the system a thorough visual inspection. Is the battery case solid and filled properly, or is it low on fluid, or maybe cracked or drained of all fluid? Are the connections at the starting motor and the relay clean and tight? Do you see any pinched, burned, or disconnected wires? Is the alternator drive belt extremely loose, or even broken, or missing completely? Do you have a blown fusible link in the cranking circuit? 2 minutes spent conducting a good visual inspection of all likely parts and points that could cause the problem you are trying to solve is time well spent. The most common cause of misdiagnosis is the failure to detect loose or unclean battery terminal connections, even when the connections seem tight and clean. This gray oxide can interfere with electrical continuity. Once you are convinced that problems do exist in the vehicle's electrical power supply system, and they are more than surface problems, you are ready to start your troubleshooting. In cases of a completely dead battery, it may be necessary to substitute a good battery for test purposes. Some thoroughly discharged batteries will not accept a fast charge, even though there is nothing physically wrong with the battery. These batteries must be slow charged for 4 or 5 hours before they can be fast charged. As a rule of thumb, if a battery is charged enough to start the engine, it is okay to leave this battery in the vehicle while the rest of the charging system is being checked out. Remember, we have arrived at this point in our checkout and repair of the charging system by 2 important preliminary steps. We have verified the complaint, and we have conducted a complete visual inspection and assured a well-charged battery, if necessary, by installing a replacement battery for test purposes. As we mentioned earlier, the problem could be the battery, alternator, regulator, or wiring, including the possibility that a ground or short circuit is draining the battery. We can most quickly confirm or rule out a short circuit as the possible cause. Simply disconnect the positive battery cable and jump the connection with a test light. If the light comes on, indicating a power drain, it may only be the car's clock winding mechanism. Reconnect the cable for an instant so the clock can wind and perform your test again. The light does not light, and if there's not enough amperage drain to light this light, there's not enough to make the battery go dead overnight. The reason we don't use a voltmeter for this test anymore is because the various new solid-state components can draw a few thousandths of an amp. That's enough to show up to 12 volts on a voltmeter, but it's not enough to light this test light. We'll talk about tracking down this kind of power drainage later, but on this car, the test light did not light. The battery isn't being drained by a ground or short. We can now turn to the alternator or voltage regulator as the possible source of our problem.
To help you get to the root of the problem with the least fuss and supply of special equipment, we recommend a test procedure that you can perform in minutes with a voltmeter. We'll demonstrate the procedure first on another car that we're not having any problem with, to show you the results when everything is working as it should.
We use the voltmeter, 0 to 20 volt expanded scale to make 3 separate measurements. We call these base voltage, no load voltage, and load voltage. We need to know battery terminal voltage with the engine not running so that we can establish a reference point, which is what we have earlier labeled as base voltage. We also need a voltage reading at 2000 RPM with minimal electrical load to see if the low side of the regulator is working okay. Then we need a voltage reading at 2000 RPM with heavy electrical load to see if the high side of the regulator is working okay. You see, the regulator is actually a two-stage device. One portion of the regulator tells the alternator how much to charge when there is only a small amount of electrical power being used by the vehicle. The other portion of the regulator tells the alternator how much to charge when there are heavy electrical loads on the system. Checking regulator action in only the high or low operational mode is only doing half a job. We need both readings before we can pass or reject a specific alternator regulator. Connect a voltmeter across the battery where it will remain throughout the three-point test. Make sure that the meter jaws or probes get a good bite on the battery terminals and observe polarity. That is, if the meter reads downscale, reverse the leads. Take a meter reading and record it. In this case, we read 12.8 volts. This is our base voltage, and remember that it was taken with the engine not running and no load on the system. Start the engine and run it at 2000 RPM using only the electrical load requirements for ignition and alternator field. As the engine runs, voltage increases. When the meter indicator stops climbing, a short time later, take a reading on the voltmeter. If this reading is not more than 2 volts higher than the base voltage reading, the low stage of the alternator regulator is working okay. We get a reading of 14.3 volts. To see how our readings would look at this point, note that base voltage is 12.8 volts and no load voltage is 14.3 volts. This means that there is not more than a 2-volt difference between them, with the no load reading being the higher of the two. Our electrical power supply system is checking out nicely at this point. Now let's put a heavy electrical load on the system so that the alternator really has to work. But in order for it to do its job, it must get the right signal from the upper stage of the regulator. We'll be checking 2 things. Is the alternator up to the job at hand? And is the upper stage of the regulator working okay? We make this test by turning on the heavy draw electrically powered accessories, the heater or air conditioning on high, and the headlights on high beam. Then we take our voltage reading at the same 2000 RPM. Under this condition, the meter should drift downward. When its downward movement stops in a few minutes, our voltmeter reads 13.6 volts. Here again, our system is checking out fine because the load test, which we have just done, calls for the voltage to remain at least 1/2 volt higher than the base voltage. And there you have it in a nutshell. Our base voltage was 12.8 volts. Our no load voltage was not more than 2 volts higher than our base voltage. And finally, our load voltage was at least 1/2 volt higher than our base voltage.
At this point, we can say with authority that our alternator and our regulator are working according to design specifications. Now let's go back to our problem vehicle and see how our 3-point voltmeter test works.
Our base voltage checks out at 12.3 volts. Our no load voltage checks out at 12.9 volts. This reading is less than the maximum 2 full volts difference, but it's low, so we know right off the bat that we might have alternator or regulator trouble. We go on to our load test and get a reading of 12.5 volts. This is bad news because our load voltage should be more than 1/2 volt higher than our base voltage. Our load voltage is only 2/10 higher than base voltage. To sum up, the difference between our base voltage and our no load voltage is a mere 6/10 of a volt. It's in the okay range, but only 6/10 higher is on the very low side. The difference between our base voltage and our load voltage is 0.2 of a volt. It should be not less than 1/2 volt. So it is apparent that we have power-producing problems with our system. The problem now at hand is to determine whether we have a problem with the alternator or the regulator. Maybe the regulator is sending out good signals, but the alternator is not responding properly. Or maybe the regulator isn't sending good signals. Let's find out. Alternator output depends upon two major factors: the speed at which the rotor is driven and the strength of the current flowing through its field windings. In general terms, the higher the rotor speed, or the stronger the field current, the more the alternator will produce. We run our operational checks at 2,000 RPM engine speed, so for our test procedures, only field current is variable. To see if the alternator is capable of putting out rated capacity, we disconnect the leads from the regulator. This takes the regulator out of the system, and the alternator doesn't know if it should charge a little or a lot. In fact, it should have a difficult time doing either because it should be receiving no field current. To see just what the alternator can do, we give it all the field current it wants. We do this by connecting a jumper wire between the positive battery post and the field terminal on the removed connector. This application of the jumper wire bypasses the regulator's control over the alternator, and with the engine operating at 2,000 RPM, we should get all the output the alternator is capable of. We note, however, that our alternator output remains at 12.5 volts under the load. In other words, the bypassing of the regulator and feeding full battery voltage to the rotor field windings did nothing to improve alternator output. At this point, we strongly suspect a faulty alternator. Now let's do a second bit of table turning and assume that with the jumper wire installed, our alternator responded beautifully by putting out voltage at or near its rated capacity. In this case, we suspect a faulty regulator, one that has been giving the alternator bad signals so that it couldn't do its job right. Replacing the regulator is the obvious fix. To sum up our checkout at this point, the electrical power supply system must pass 4 voltmeter tests, 3 with the regulator in the system and 1 with the regulator bypassed by means of a jumper wire. If our 3 voltmeter checks show trouble with the alternator or its regulator, the jumper wire is used to bypass the regulator.
If the alternator responds to the jumper, the regulator is the likely source of trouble. If the alternator does not respond to the jumper, the alternator is the likely source of trouble. It is possible to encounter bad wires in the charging system harness. Connect the voltmeter between the battery ground post and various points on the regulator connector to make sure our trouble that appears to be the alternator is not simply a broken, pinched, or otherwise damaged wire. Your book has more details of this test.
Another situation that can occur in the field is an overcharging electrical power supply system. This is not a chronic or even a common occurrence, but it can happen. If a battery uses a lot of water and an owner complains of a won't crank condition that is almost immediately corrected by a proper filling of the battery, you can safely suspect that the charging rate is much too high, probably caused by the regulator points sticking to deliver full field current to the alternator at all times it is in operation. We can check out this possibility with our voltmeter setup. First, we take our base voltage, which of course is battery terminal voltage without the engine running and with no load on the battery. Let's assume we get a reading of 12.9 volts. Next, we make the no-load test at 2,000 RPM and get a voltage reading of 15.3 volts. This is more than 2 volts higher than the base voltage. With this kind of reading, it is evident that we have a case of an overcharging alternator on our hands. As the first step in checking out the cause of the overcharging condition, we connect a jumper wire between the regulator base and a known good ground. We do this because we know that an improperly grounded regulator cannot feed reliable signals to the alternator. If the alternator output voltage comes down to within limits with the regulator grounded effectively, stop the engine, remove the jumper, and clean and tighten the regulator base attaching screws. Then repeat the test for possible overcharging. If the use of the regulator base grounding wire doesn't bring the alternator output back down to specifications, disconnect the regulator from the system, and without a jumper wire from the battery to the alternator field, plus no regulator in the system, the alternator should receive no field current, and its output should drop to virtually zero. The voltmeter, of course, will show base voltage only. If the alternator output stays high with no obvious source of field current, it is getting field current from somewhere. Probably the field wire and A+ or battery wire are touching in the harness. Do not expect to run into cases every day where alternators overcharge with no apparent source of field current. It's such a simple check to make, however, that it isn't worth overlooking when you run into that highly unlikely but possible condition of alternator overcharging. Up to this point, we have discussed how to pinpoint alternator and regulator trouble in the electrical power supply system. We have illustrated the use of the voltmeter in making the three simple checks: base voltage, no load voltage, and load voltage. We have also detailed what to expect in the way of readings from good and bad charging systems. We have also covered the use of the jumper wire in isolating trouble to either the alternator or its regulator. Then we showed the jumper wire being used to make sure the regulator had a good grounding of its base. And we mentioned that without a good ground, even the best of regulators cannot supply reliable information to the alternator. Finally, we discussed a condition whereby an alternator can be overcharging, even with the regulator completely out of the system and the alternator field getting no apparent source of field current.
We are now ready to talk power drainage and batteries. If you would like to review the voltmeter test procedure before we move on, simply set the counter back and follow in the appropriate section in your booklet. Some owners experience trouble with their electrical power supply system because of such minor things as an automatic trunk light that stays on all the time, even when the trunk lid is closed. Such cases of battery drain can be difficult to locate and are often the real causes of unnecessary replacement of alternators, regulators, and batteries.
As we mentioned, the best way to check for battery drain is to remove the positive battery cable from its battery post and connect a test light between the battery post and cable terminal. This places the light in series with the battery. If the light comes on, reconnect the cable for an instant just in case the clock winding mechanism was causing the current draw. Now any current flow through the light with all electrically powered accessories off indicates a drain on the battery, one that could weaken the battery overnight so that the engine is slow to start in the morning. Should a condition of battery drain be noted by the test light, first try to stop the current flow by removing one fuse at a time. If you pull a fuse and the drain stops, you know you have trouble in the circuit that is protected by that fuse. If removal of all fuses doesn't stop the battery drain, disconnect the harnesses at the quick disconnects. Disconnect one harness at a time until the drain stops. Then trace down the cause of the drain in the circuit or circuits supplied by that harness. It is generally agreed that you cannot accurately test a discharged battery. This means that if a customer complains of a dead battery, battery rundown, or a weak battery, and your 3-point voltmeter test indicates the alternator and regulator portion of the system are okay, you suspect battery problems. If the battery is discharged, it is probably best to remove it from the vehicle for a slow charge. If the battery is charged, or after it has been properly recharged, probably the best overall test for the battery is a high-rate discharge test using the Rotunda Battery Starter Tester ARE 1631. With the battery in or out of the vehicle, place a load on the battery with the tester that is equal to 3 times the battery's amp-hour rating. For example, a battery with a 45 amp-hour rating should be tested under a machine load of 135 amps. Length of test time is not more than 15 seconds. If after this period of time, battery terminal voltage does not fall below 9.6 volts, the battery can be considered in satisfactory condition and fit for further service. A battery that cannot pass a high-rate discharge test when it is in a full state of charge is not up to snuff and should be replaced. We will admit, however, that there are probably a lot of batteries currently in daily service that could not pass a high-rate discharge test. These batteries are doomed to failure. Of course, no one knows exactly how quickly.
As a general rule, customers do not like to take chances with their batteries. If you stick to your high-rate discharge test as your guideline to battery condition, you might replace some batteries that could have been nursed along for a few more weeks. But is the risk really worth it?
Batteries are seldom repaired in service. Likewise, regulators. Alternators are another thing. Complete alternator testing procedures are included in the 1975 supplement to your car diagnosis manual. There are 11 pages of these tests right near the front of the charging and starting system section. Alternator repair procedures are included in Volume 3 of your shop manual, Section 31. Let's recap. After confirming an apparent charging system problem, check the battery connections very thoroughly in your visual inspection. As we mentioned, overlooking this is the most common cause of misdiagnosis. In the first test we showed, if the test light doesn't glow, we can rule out a ground or short as a possible cause of battery power drainage. In the three-point test, we find out if the problem is with the alternator or regulator. If the system fails the three-point test, we bypass the regulator to find out which component, alternator or regulator, is at fault. With the high-rate discharge test, we are able to check the condition of the battery, its ability to hold a charge.
If the charging system passes all these tests and the battery still goes dead, the problem isn't with the charging system and further diagnosis is in order. As we mentioned in the introduction, the charging system depends on several components: battery, alternator, regulator, and wiring. Misdiagnosis can happen because problems with any of these components can cause the same symptom, a dead battery. With the sequence of tests featured in this program, you can isolate a charging system problem and fix it right the first time.